I was just thinking, like obviously, the first topic that you learn in A level is, well, aside from the basic recaps of indices and surds and just some of the basic coordinate geometry that you learn at GCSE, the first actual meaty topic that you learn in A level is calculus. And I remember when I was about just finishing high school, just over the holidays, I was like, what the heck is this thing? Because I heard a lot about it. I don't know what the heck it was, and I looked at some YouTube videos and they were just sort of giving me an outline as to what the heck it is. Oh yeah, look at this. That was that question, man. Can't be bothered with it. Given up on it. Probably look at it later on. Probably the answer will come to me, but we'll see what happens with that. But anyway, calculus, there's differentiation and there's integration. I'll leave that alone for now. I'll look at this bit for sort of today's little session, if you like. Differentiation is all about gradients of curves. So basically, let's have a graph that we'll refer to. So you've got a graph that looks like this, yeah, something like that. And I'll refer to this graph when I'm talking about both of them, but I'll do this one first. So this graph, if I want to work out the gradient of this graph, or the function, you can call it, anywhere on this graph, obviously I want to find out the gradient of the particular function. So for example, say at x equals 1, I want to work out the gradient of it. It's basically going to be equal to the gradient of the tangent line. So I'll draw a tangent line there. And I want to work out the exact gradient at that exact point x equals 1. And obviously you might break out a ruler and then do the change in y by the change in x. And you might remember it being referred to as dy by dx, or delta y, delta x, where delta represents the change in y by the change in x. And the common sort of the common way of referring to it is dy by dx, where y is obviously the original function, so that's possibly looks like a cubic possibly, and so that's basically the thing you use to define the gradient of the particular function y. So I'll just do a quick few examples of how you work out the gradient function. So let's say y equals 3x squared. That's just a random one, it's not that one because that's obviously a quadratic. That looks more like a cubic. But if I want to work out the gradient of this function, what I do is look at this power here, you bring it down, i.e. you multiply by whatever the coefficient of that term is, of that x squared term. So it becomes, so dy by dx would be 2 times by the 3, which is 6. And then what you do is you decrease that power of 2 by 1, so it just becomes x to the power of 1, or obviously 6x. And what that is saying is that if I have this function here, let's just draw it. If I have this function, that's going to look something like this, obviously. Probably not the best drawing on the planet, but you get the idea. That looks almost as if it's turning back on itself, which is wrong. It should look a bit more like that. What it's saying is that no matter where I choose on here, the gradient of this point here, the gradient at this point, is just going to be, so say the x coordinate is 2. The gradient at 2 is just going to be 6 times by whatever that x coordinate is. So at this point the gradient is 12. If I come back here and I want the gradient at this point, say this is, I don't know, minus 1.5, why not be awkward? It's going to be 6 times by minus 1.5, so the gradient at this point is going to be minus 9. Okay, and as you get closer and closer to here, obviously the gradient here is a flat line. So I'm expecting the gradient to be 0, and of course at x equals 0, if I do 6 times by the 0, because that's the x coordinate, right? 6 times by 0, that does tell me that the gradient at that point is 0, i.e. just a flat line. So that's the idea. Let's have another one. Let's have y equals, let's go a bit mental, why not 7x to the 6. Of course, I'm just going to do 6 times by the 7, so dy by dx is going to be 6 times 7 is 42. X to the power of, and of course remember just to bring that down by a 1, so it becomes 42 x to the 5. And of course if you have something a bit more awkward, like say y equals bx to the 5 add 3x to the 4.2, seems a bit clapped out, but let's just do the exact same process. Dy by, can you see this? let's go, there you are. dy by dx is going to be 5b x to the 4, exactly the same idea. Remember, 5 comes down, bx to the power of 4, you just decrease the power by 1. Here you can do exactly the same thing. So 4.2 times 3 is 12.6. Pretty fast, aren't I? X to the power of 4.2 take away 1, that's 3.2. So that's it. That's literally just the idea for differentiation. For integration, it's a little bit different. So remember, differentiation is all about gradients and stuff like that. So if you remember, when we did look at curves and sort of areas under them and gradients of curves and things right towards the end of the GCSE spec, integration is the other one. So if you remember that we did the gradients and we also did the areas under the curve, integration is all about the areas under the curves. So when you do your A levels, you're going to spend a lot of time doing this stuff, a couple of months doing this, maybe 1 month, 2 months, I'm not sure. And then you're going to move on to a bit of integration. Now this is just about areas underneath the curves, and it's just the inverse process of this. So if I want, so say for example, this curve here is y equals 3x squared, not that one, maybe that one. If I want to work out the area of, say, can you see this? Yeah, so say I want to work out the area, I'll use a different color pen. Maybe I want the area here. So say this is 3 and this is 0, obviously. If I want the area of this green bit I'm shading in now, first of all, I do the inverse process of what I've been doing here. So I kind of imagine I'm here and I want to get back up to there. So I'm going to work out, so I'm going to integrate. We say that's the integral function. Oh, I'm not sure how exactly what exactly you call that, but you integrate y between the two x coordinates, so 0 and 3, 0 and 3, with respect to x. And what that's doing is basically adding up all these heights, all these infinite like sort of heights. If you sort of break this down into tiny strips, you're adding up all of them between 0 and 3, and the width is going to be sort of a dx, which is basically an infinitesimal sort of small size. So that's what you're doing, you're adding up these tiny strips, and that's what this is basically telling me. And that obviously gives me an area. So this here is the area of each singular strip, where the height is y and the width is dx. So I do that. If I integrate y now, so I can just substitute this in because y is equal to 3x squared. So integrate 3 between 0 and 3, or the function 3x squared with respect to x. That's how you pronounce that, with respect to. And we're just going to do the opposite now. So here, if you remember, when we were differentiating this function, we did 2 times by 3 and we subtracted 1 from that. We're going to do the opposite. So this time, so almost imagine it as a function machine. So if the process was to, first of all, multiply power and then subtract 1 from power, and that gives you the dy by dx function. If I want to go backwards now, if I want to go backwards and do the inverse process, i.e. if I want to integrate, I'm going to do the opposite of this one. I'm going to add 1 to the power, and then I'm going to divide by whatever this new power is. So I'm going to add 1 to this power, add 1 to 2, that's just going to be 3, obviously, and then I'm going to divide by it. So I'm going to end up with, well, 2 add 1 is 3. If I divide the whole thing by a 3, so the new power is going to be 3, of course. If I divide 3 by this power of 3, 3 divided by 3, well, that's just 1. Okay, and a lot of time you'll see this one because it's a nice one to choose in terms of exams and stuff, because it sort of simplifies nicely. And that becomes, well, we want that between 3 and 0, remember, because that was where we wanted the area between. So this is now being integrated. That's going to give me x cubed between 3 and 0. I'll substitute in 3, I get 27, and I take away whatever this value gives me. So I do 3 cubed, take away 0 cubed, and that's obviously 0. So the area of this green bit is equal to 27 square units. That's it. Enjoy.